Hi, welcome back. Welcome to Unacademy, India's largest online learning platform. About myself, I G Venkata. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 plus students for their GATE examination. At present, I am pursuing my PhD in JNTU Kakinada in VLSA domain. So first, we check how to get the Unacademy learning app into your device. Just go to Play Store. There type Unacademy. Okay, you get the Unacademy learning app like this. Okay, just click on the install button. Then it will install the Unacademy learning app into your device. Okay, if it is in your device, it's fine. Otherwise, install it. Now, see, once you open that Unacademy learning app, you get what are the different courses handled by the top faculty in India in Unacademy. Okay, and different courses and the faculty available for that course. Okay, here you observed or not, here are the few of the top educators. Tiwari sir from IIT, one of the IIT topper. Ankit Goyal sir, he is All India first rank twice in electrical department. Jaspal Singh sir, he is ex-IAS officer. And Sanjit Jain sir, he is from computer science faculty. And here are few more faculty who are handling the classes here. And now I'm happy to say that we are going to launch two new batches for mechanical. See, there is a SN batch for GATE 2023. This is for mechanical department. Now it is going to start from 8th February 2021. Here are the top faculty handling the classes in this mechanical engineering department subjects. And one more, don't forget to use my code VRAW10 during subscription to get 10% of discount. This is SN batch for GATE 2023 and the Evolve batch for GATE 2022. There is Evolve batch for GATE 2022. This is also going to start from 8th of February. Here are the faculty handling these subjects for mechanical engineering. And there is a civil engineering new batch. Okay, SN batch for GATE 2023. Here are the top faculty handling the subjects in this civil engineering. So this batch also going to start from 8th of February. Okay, please don't forget to use my code during subscription VRAW10 to get 10% discount. And next there is a Evolve batch for GATE 2022 for civil engineering. Here are the top faculty handling the subjects in this, and this is also going to start from 8th of February. This is a batch D. Already A, B, C batches are running. Now this is the batch D. And next for computer science and information technology, there is a Evolve batch for GATE 2022. Here are the few of the top faculty handling the subjects for computer science engineering. Okay, and this batch also going to start from 8th of February 2021. And there is a SN batch for GATE 2023 for electrical engineering. This batch is already started on 1st of February. Okay, here are the top faculty who are handling the subjects in this. And again there is a Ascend batch. Now this time this is for ECE, electronics and communication engineering. This batch also already started from 1st of February. And next there is a Evolve batch for electrical engineering for GATE 2022 students. Okay, this batch is already started on 1st of February. And again there is a Evolve batch for GATE 2022. This time this is for electronics and communication engineering students. Here are the top faculty handling the subjects in this. This batch is going to start from 1st February 2021. Already it is started last week itself. Now again, a chemical engineering department. This is a eval batch for GATE 2022. Here are the top faculty who are handling the chemical engineering subjects. Okay, this batch is already started 25th of January. If any of your friends are away outside who are studying the chemical engineering, okay, please inform this one to them, because outside getting chemical engineering training is not possible. It is very difficult to get the faculty. Okay, so you must thank for, and you must thank to Unacademy to provide such a good faculty for even chemical engineering also. And now we check what are the different disciplines available in Unacademy for GATE and engineering service. Here is the mechanical engineering, electrical, civil, production and industrial, instrumentation, chemical, computer science and IT department, next ECE department. Okay, these are the different disciplines available in Unacademy. Now there are two types of subscriptions. First one is a plus subscription, second one is iconic subscription. Plus subscription is the basic plan. Plus subscription is basic plan, and iconic subscription is the next level of the basic plan. In this, you get a personal coach. A personal coach is assigned to you. Okay, that coach is going to guide you throughout your course. In both the case, few common points are: your classes are taken care by the India's best educators, and there are interactive live classes, structured courses and PDFs are available to you. They will provide that one to you, and the live tests and quizzes. In iconic, so once live test and quizzes are completed, okay, so once after completion of the examination, okay, they will analyze your paper from first line to last line, whatever the answers you've given. Based on that, they will prepare where you are strong and where you need more preparation, where you are committing mistakes, what are the common mistakes you are doing. Everything they will analyze. Okay, they will analyze and they will guide you. For that, your personal coach is going to support for that. Okay, that is the duty of the personal coach. And personalized test analysis, this is the point. And they will provide a study planner to you, proper study plan. Based on that, they will prepare a study plan to you proper, and they prepare a study material also. Okay, just to how to follow them, not more than that. By doing all this, definitely you get success in your examinations. Okay, don't forget plus and iconic. Plus is the basic plan, iconic is the next level of the plan. In this, personal coach is available for each and every individual student. So we check just once about plus plan. In plus plan, there are 1 month subscription, 3 month subscription, 6 month subscriptions, 12 months, 18 months and 24 months. Okay, and here the beauty is EMI optionals available for this. EMI optionals available for this. Okay, and if you check the 10 month subscription, 12 month subscription, it is 30,250 rupees. After using my code VRAW10 during subscription, you get 10% discount. After 10% discount, it became 27,225. Okay, if you compare this amount with the amount what you are spending throughout the year for traveling purpose, where you are taking the classes outside, more or less this is close to that amount, hardly 3 to 4,000 variation. Okay, don't forget that. And to go to the iconic, this is the 12 months plan, 50,250, and for 2 years or 24 months it is 74,000. Now after using my code VRAW10 during subscription, VRAW10, you get 10% discount. You get 10% discount. So that is 45,225 rupees only. Okay, this amount is more or less equal to the amount what you are paying at outside institutions. Okay, but there it is very difficult to get a interact the faculty personally, because faculty is always try to covering their syllabus, busy with the covering their syllabus within the stipulated time, and even lunch break is hardly you get 1 hour. Okay, so if you have any doubts, you have to ask those doubts in class itself. Some of the students feeling shame to ask the doubt to the faculty. So these are the different criterias. So but in case of this, you have a personal coach, you can share everything with him personally, freely. Okay, personal coach will note the point what you are giving, a respective, it was forwarded to the respective faculty will come and clarify your doubt. And one most important thing is, no need to move anywhere, just you have to sit at your home and you listen the classes. That is the most important thing. No need to move anywhere. Okay, so my dear students, please think once of it. Don't waste your time. Whatever thing is happening at outside, but your learning process cannot be stopped. That is the motive first. Okay, who are doing hard work at this moment, definitely they will get success. Clear? Thank you. Now we are going to our next topic. Now we are going to do some problems on semiconductors, important model problems on semiconductors. Okay, so this is the first problem today. See this problem. The figure below shows the doping distribution in p-type semiconductor in log scale. So that means this is the log scale. This is the doping distribution. This is 1 micrometer they given here. It is 2 micrometers. Log scale in the sense, for example, if I am taking this is the point x1 and this is the point x2, log scale in this sense, we can write log x1 equals to 1 micrometer. So this is base 10, and similarly log x2 base 10 equals to 2 micrometer they given, 2 micrometer. From this we can write x1 is 10 power 1 micrometer, and we know the value of 1 micrometer. 1 micrometer is 10 power minus 4 centimeters. So that is 10 power 1 into 10 power minus 4 centimeter. So x1 value is 10 power minus 3 centimeters. That is 0.001 centimeter. That is the value of x1. Now I am going to x2 value. For x2, from this x2 value is 10 square micrometer. So that is a 10 square into micrometer is 10 power minus 4 centimeter. So now it became 10 power minus 2 centimeters. It is 0.01 centimeter. Okay, next. So far we extracted the exact value of x1 and exact value of x2. Okay, because they given in a log scale, that is very important. Next, the magnitude of electric field in a semiconductor due to non-uniform doping. See, you observed or not, this semiconductor at x1 its doping is 10 power 14 per centimeter cube, and at x2 its doping is 10 power 16 per centimeter cube. That means it is not uniformly doped. There is a non-uniform doping. Due to this non-uniform doping, an electric field is developed within the semiconductor. So you need to calculate that value. First of all, we go and derive an equation for that. after that we substitute values in that. See, first of all, your semiconductor is no external electric field is applied to that. That's why there is no current. So no current in this sense. Current density of that semiconductor is 0. So in that, this is a p-type semiconductor. So J drift by P. Okay. Current density by holes equal to 0. That means J equal to 0 in this electron current density plus hole current density. So electron current density is 0 as well as hole current density also 0. Now I am taking Jp equal to 0. So in that we have two components, drift component and diffusion component. Drift component of hole plus diffusion component of hole. And we know the drift component, J drift. Now I am going to J drift by hole equals to drift component I am writing. So that is P into, or take it as P naught into Q into mu P into applied electric field. Okay. Next, diffusion component. Diffusion by hole is minus Q into dP into dP by dx. So I am taking P, that's why here also I am taking it as P. Now sum of these two equal to 0. Therefore P into Q into mu P into electric field is drift plus diffusion. Diffusion is minus of, that's why it is minus Q into dP into dP by dx equals to 0. Current density by this total current density or current density by holes is 0. Now from this I am taking this one this side. Therefore P into Q into mu P into E equals to Q into dP into dP by dx. And in this Q gets cancelled. Okay, we need to get the electric field E. Now take this P this side, at the same time mu P also this side. Therefore electric field E is equals to dP by mu P into 1 by P into dP by dx. So this is the equation. dP by mu P, we know that from Einstein relation we can write that dP by mu P is Vt. So from this electric field E equals to dP by mu P is Vt into 1 by P into dP by dx. This is the standard equation. Now based on your problem you need to change that. Okay, just go back to your problem and check the data what they given. See, at x1 Na value is 10 power 14 and at x2 Na value is 10 power 16. 10 power 14 and 10 power 16, that is Na. Now if you observe this equation, E is Vt 1 by P dP by dx. So I am replacing this P by Na and that too Na of x, because Na is the function of x. So therefore E is equals to Vt into 1 by Na into dNa of x by dx. This is the expression for this problem. Now in this problem equation we know dNa by dx. dNa by dNa of x by dx we can write Na2 minus Na1 by x2 minus x1. No problem. But here we have 1 by Na. In place of this Na, which one you need to take? In your plot they given two values of Na. One is 10 power 14 at x1, another one is 10 power 16 at x2. Which one you need to take in this two? That is the problem. Okay, so for that I am going to changing a little bit modification in my equation. That modification is, now I am going to write is Vt into, see, 1 by x into dx by x dx, or 1 by y into dy by dx is nothing but a, okay, differentiation of ln of x, d by dx of ln of n a. That's it. D by dx of ln of na. Now if you differentiate that, you get 1 by na into dna of x by dx, or you can take it as x also, it's not an issue. So for easy understanding purpose I remove this x. Now this is the expression. Now we can write this one is Vt into ln of na2 minus ln of na1 by x2 minus x1, x2 minus x1. Just substitute the values. E equals to, we know the Vt value 26 millivolts approximately, 0.026 into ln of, they given na2, this is the plot they given here, 10 power 14, na they given 10 power 16 here they given. So 10 power 16 minus ln of 10 power 14 by x2 minus x1. So we know the value of x2. x2 is 0.01 minus x1 is 0.001. Just simplify this. It is 0.026 into, see, it is 16 ln of 10 minus 14 into ln of 10. So ln of 10 is common. Now it is 16 minus 14 is 2 into ln of 10. Ln of 10 value is 2.3 approximately, by 0.01 minus 0.001. So we check the value of that. 0.01 minus 0.001, that is 0.009. So it is, now just simplify this, into 2 into 2.3 divided by 0.009 is a 13.28 volt per centimeter. That is the electric field. But they ask the, in problem they asked in terms of kilovolt per centimeter. Now it is 0.0132 kilovolt per centimeter. So that is the answer. Yeah, see this here, they ask clearly in terms of kilovolt per centimeter. Okay, so that is a 0.0132 kilovolt per centimeter. That is the electric field. See, in this problem what we have to observe is, due to non-uniform doping, an electric field is existing in a semiconductor. Just we calculated the electric field value, we derived the equation for that. Even though after deriving the equation, the given data is not supporting for direct substitution. For that, whatever the E equation, electric field equation there we have, I converted that in the form of log. Once I converted that in form of ln of differential, now it is supporting the direct substitution of values. Then I substituted the values into that. Okay, so like this you have to solve the problem. Okay, next. So I'm going to next problem. So now this is our second problem. See, a piece of silicon is doped uniformly with phosphorus. So phosphorus means it is a donor impurity material with a doping concentration of 10 power 16 per centimeter cube. So the given Nd value is 10 power 16 per centimeter cube. The expected value of mobility versus doping concentration for silicon assuming full dopant ionization is shown below. So this is a plot between mobility versus doping concentration Nd. This is the plot they given. Okay, the charge of an electron 1.6 into 10 power minus 19 coulomb. The conductivity of silicon sample at 300 Kelvin is. See, we know the conductivity of a silicon sample. Conductivity of N type is written as Nd into Q into mu N. Nd they given clearly, it is a 10 power 16 into Q 1.6 into 10 power minus 19 into, now we need mobility. See, in this problem directly they did not given mobility, that mobility is given in terms of a plot. Here two plots we have, one is a dotted line, other one is a thick line, complete line. Now clearly in brackets they given continuous line is mobility of electron and dotted line is mobility of hole. This is N-type semiconductor, that's why we need mobility of electrons. So we need to concentrate on thick line. So they given mobility versus Nd doping. So they given doping here on x-axis 1.e plus 13, 1.e plus 14. The meaning of this one is 1 into 10 power 13. That is the meaning of this. And it means 1 into 10 power 14. This is 1 into 10 power 15. That is the meaning of this. Per centimeter cube, everything is. Now, the doping in our problem is 10 power 16 per centimeter cube. Okay, this is 10 power 15. Here is 10 power 16. 1 into 10 power 16 per centimeter cube doping. At this point, this is the intersecting point. Here it is. Now, approximately its value is 1200. Now, the required mobility from plot, I taken the mobility value is from plot. Therefore, mu n is 1200 centimeter square per volt to second at doping of 10 power 16. Now, just substitute the value of it into 1200. Now, simplify this. So 16, 18, it is you can write it as 1.2. So 1.6 into 1.2. It is 1.92. 1.92 ohm to centimeter inverse. That is the conductivity. Ohm to centimeter inverse. That is the conductivity. Okay. Next problem. Yeah, this problem. So now this is the third problem. See, the energy band diagram and energy density profile N of x in a semiconductor are shown in the figure. Assume that N of x equals to 10 power 15 into e power q alpha x by kt per centimeter cube, with alpha equal to 0.1 volt per centimeter and x is expressed in centimeters. Given kt by q 0.026, dn 36 centimeters square per second, and d by mu is kt by q. Electron current density in amps per centimeter square at x equal to 0. At x equal to 0 they want. Okay, at this point x equal to 0, what is the This is the concentration of electrons, ln of nx, log of n of x. This is the energy at x equal to 0. So at x equal to 0, what is the current density? Okay. See, by seeing this plot, your doping is changing with respect to distance. It is not a constant. That is not a constant. Changing with the distance. That means there is a concentration gradient exists in that. Due to that concentration gradient, you get some diffusion current density. Next. See, your energy of your EC energy, EV energy, both are not equal. That means not they are not flat. They are maintaining some bending. This bending represents electric field is directed this side. So an external potential is applied across this. This is the meaning of representing energy levels like this. We have another problem. There we discuss in detail about the representation of energy levels with a little bit bending. Okay, what it represents. So due to this, we can conclude there is a drift current exists in that. Due to this, there is a diffusion current exists in that. Now, total current density is J drift plus diffusion. Drift plus diffusion. They given energy density profile n of x. That means it is a n type semiconductor. Now I am writing the equations for this. First I am going to calculating the diffusion. So J diffusion by n type electrons is, our equation is Q into dn into dn of x by dx. But we need at x equal to 0. Everything we need at x equal to 0. So this one also at x equal to 0. First I am going to calculating dn of x by dx. So the given n of x value is, so given n of x is 10 power 15. N of x equals to 10 power 15 into e power q alpha x by kt. Now I am taking this q. Okay, leave it. Now this is the value of n of x. We need dn of x by dx. That is 10 power 15 is constant into differentiation of e power x is e power x. Sorry, into differentiation of this x. So it is a q into alpha by kt. But we need this one at x equal to 0. So our requirement is dn of x by dx at x equal to 0. Just substitute x equal to 0 in this. So that is 10 power 15 into q alpha by kt into e power 0. E power 0. E power 0 is 1, we know that. Now just simplify this. Therefore, dn of x by dx at x equal to 0 is 10 power 15 into q into alpha by kt. So now I am substituting these values in this. Therefore, J diffusion is J diffusion by n is q into k dn into dn by dx. So dn by dx is q into alpha by kt. Yeah. So it is Q into alpha by KT. So now it is Q into dN into alpha by, say it is a 1 by KT by Q, that is nothing but a VT. Okay, and we know, so in that problem they given mobility to you. Okay, they did not provide, so d by mu is KT by Q. Okay, now just substitute the values in this. Q 1.6 into 10 power minus 19 into dn value, that is 36 or 32, 36. dn value they given it as 36 into alpha value they given 0.1 by into 1 by Vt 0.026 they given clearly. Just simplify this. Now okay, so Q into dn of x by dx at x equal to 0. Okay, I calculated individual values, fine. So yeah, we forgot one thing here. 10 power 15 is there, we need to substitute that value. Here 10 power 15 is there. Now it is okay, into 10 power 15. Now simplify. This is 19, it is 15, 10 power minus 4. You can write this is 26, and this is 10 power minus 1. So now 10 power minus 1, now it is 3.6. So now it is 1.6 into 3.6.1, it is 0.36. 0.36 by 26. So I am simplifying this. 1.6 into 0.36 divided by 26. So that is a 22.1 milli, 22.15 milli amps per centimeter square. That is the diffusion current density. Next we need to calculate drift current density. Next part is drift current density. Okay. So J drift is P into, sorry, N, it is N into, that means they given N of X, so N of X into Q into mu N into E. So E of X, why I am taking E of X is it is not uniformly doped, okay, because of some electric field is existing at the junction. Now we have an equation for electric field, and that too we need this one at x equal to 0. At x equal to 0 I want everything. This one at x equal to 0, this one also at x equal to 0. First I am taking N of X value. So N of X they given 10 power 15 into e power q x alpha by kt. Now at x equal to 0, from this N of X at x equal to 0 is simply e power 0 is 1. So it is 10 power 15 per centimeter cube. That is the value for per centimeter cube. That is the value of N of X at x equal to 0. Next we need E of X. So already we derived an equation for E of x previously, that is for p-type semiconductor. Now E of x is kt by q into 1 by n of x into dn of x by dx. One important point here is you get negative for this. Why? Because during the calculation of electric field for a p-type material, p-type semiconductor, just I'm going to previous slide, previous problem what we completed. In this we taken drift plus diffusion by hole. So drift plus diffusion, in that diffusion we have a negative sign. It is after placing these two here, it became negative equal to 0 minus of this one, then it became this one equal to this one. But in case of n type it became positive. Okay, that's why there I get negative. Yeah, now this side I will derive that equation. See, J drift plus J diffusion equals to 0 to derive electric field existing. So this is J drift is P into Q into mu P into E equals, sorry, it is a n type semiconductor. So for n type, n into Q into mu n into E plus diffusion Q into dn by dx equal to 0. Just take this one that side, then you get E is equals to minus kt by q, that is nothing but a vt dn by mu n into 1 by n into dn by dx. That is the expression. So this is nothing but our vt. So E can be written as now minus vt into 1 by n into dn by dx. That's it. That is the electric field. Now I'm going to using the same expression here. Now substitute the values. Minus kt by q. So kt by q, and that too we need this one at x equal to 0. Okay, first E of x is kt by q is nothing but a vt into 1 by n of x. So 10 power 15 into e power something alpha q x by kt something into dn of x by dx. Already we derived dn of x by dx at x equal to 0 already. It is 10 power 15 into q alpha by kt. So at x equal to 0 we need, directly I am substituting that one here at x equal to 0. At x equal to 0 here it became 0. So it became 1 into, so we have a value for dn of x by dx at x equal to 0, that is 10 power 15 into q into alpha by kt. See, this 10 power 15 gets cancelled. So this Vt and this 1 by kt gets cancelled. It is minus alpha. So minus alpha they given 0.1 volt per centimeter. Alpha is 0.1. Now we know the E value. Just take that E value, substitute in this equation. Therefore J drift equals to n of x at x equal to 0 is 10 power 15 into q into 1.6 into 10 power minus 19 into n of x into q into mu n. See, mu is nothing but they did not give any mobility value to you, but we know one thing from Einstein relation, d by mu equals to vt. Okay, so from this mu equals to d by vt. So d they given 36, mu 0.06 0.026. Just substitute the value here. 36 divided by 0.026 into dn by dx, sorry, into electric field, I think so. Yeah, into E of x at x equal to 0. That is minus 0.1. Minus 0.1. Now simplify this. First it is negative. Now 15. So it is 10 power minus 4. Now this is within this it is 26. It is 10 power minus 1. 10 power minus 1 can be written as it is 3.6. Now it is 1.6 into 3.6 into 0.1 by 26. That is 0.16 into 3.6 equal to divided by 26. That is 22.1 milli minus 22.1 milliamps per centimeter square. So far we calculated a drift current density and diffusion current density. Just take both and add. That is the final current density. This is 22.15. So for this one also 22.1538. For this one also same. See, 0.36, 1.6, 1.6, 3.6. It is 0.36, but it is into 0.1 by 26 by 26. Both the case you get the same value. Because of this negative sign, J drift is 22.15 minus 22.15. 0 amps per centimeter square. That is the current density. 0 option is. Yeah, here is the option. 0. First you can conclude. They did not ask anything directly here. They asked simply, they given the plot. From that plot, first what you understand, that is important thing. Okay, after understanding you need to calculate drift and diffusion separately. Okay, so that is the procedure, and you may expect at some particular x value also. Here they given at x equal to 0. Because of that our simplification is easy. They may ask at x equal to some 0.1 centimeter or 0.2 centimeter, like that also. You should be practice such type of model problems also, just by changing the x value, how to solve that. Okay, you have to practice the simplification. And one more, physical calculator you are not getting, not possible to use in your examination. It is not allowing. Virtual calculator you have to use, and you have to practice how to use virtual calculator also. Okay, so that is the important thing. Next problem. Yeah, see, an intrinsic silicon wafer is doped with 10 power 16 per centimeter cube arsenic atoms. Okay, so that means they given N is 10 power 16 per centimeter cube arsenic atoms. If small amplitude, low frequency, alternating voltage of V in is applied across a block of this doped silicon, a current I in, small in current, a current is flowing through. Assume the block is a cube of side 5 micrometer. It is a cube of side 5 micrometer, and all the dopant atoms are ionized. Then get dou V in by dou In. Assume intrinsic carrier concentration of silicon is 10 power 10 per centimeter cube volts to second per centimeter square. Sorry. Sir, this is only per centimeter cube, sir. This is not mobility. Only per centimeter cube. 10 power 10 per centimeter cube. So it is 10 power 10 per centimeter cube. That is the Ni value of silicon. And electron mobility 1000 centimeter square per volt to second. And hole mobility 350 centimeter square per volt to second. So what they are trying to say is they have a cube. First of all, they have a cube of side 5 micrometer, of side 5 micrometer. It is a cube. Now a small voltage is applied across this. Small change in small signal is applied across this. It results a small current is flowing through this. Then they want change in small voltage by input to signal by change in small input current. See, V by change in input by change in output, it is nothing but a resistance. Dynamic resistance generally we call it because it is a change. Okay. Now we need, so this is nothing but a resistance, whatever we need. So if you want to say strictly, that is the dynamic resistance. Dynamic resistance. Dynamic resistance. Now we need that resistance of that. So resistance is nothing but a, we can write 1 by conductivity. Resistance is 1 by conductivity. 1 by, sorry, resistivity, that is. We know the resistance value, rho L by A. Now rho is 1 by conductivity into L by A. So L is 5 micrometer and A is 5 into 5 micrometer square. That means 5 micrometer into 5 micrometer. 5 micrometer into 5 micrometer. Now just substitute the values in this. And 1 by sigma is, conductivity is Nd into Q into mu N into L by A. Just substitute the values. Now R is, resistance value is, dynamic resistance is L by, it is L. L is 5 micrometer. 5 micrometer by Nd 10 power 16 per centimeter cube into Q 1.6 into 10 power minus 19 coulomb into mu N 1000 into area 5 micrometer into 5 micrometer. 5 micrometer into 5 micrometer. 5 micrometer into 5 micrometer. Now just simplify this. 5 micrometer here and here it is 5 micrometer. 16 10 power minus 19 and this one gets cancelled. So micrometer we can write it as 10 power minus 4 centimeter. Okay, now it is 5 into 1.6 is 8. It is 10,000 by 8. Okay, now it is 10 by 8. It is 1.25 kilo ohms. 1.25 kilo ohms. Here is the option. Instead of asking resistance directly, they given the problem in this file. And by seeing options also, here everywhere here you have a ohms units. From this also you can get the idea. If you are not getting idea directly, then immediately go and check the options. In option they give some code, some information to you. Like this, in this problem they given ohm. So from ohm we can easily get that we need a resistance. Okay, so like that, if your problem is not understandable to you in a proper way, direct way, then you can go back to your options. In that options, every option is having some units. Based on that units you can get some idea. Okay, now next one is, see this. An n-type semiconductor has conductivity 1 milliohm inverse centimeter inverse. Conductivity 1 milliohm inverse centimeter inverse. Okay, n-type it is conductivity 1 milli 10 power minus 3 ohm to centimeter inverse. Yeah. by compensation doping. By compensation doping, it is to be made a p-type semiconductor with the same value of conductivity. See, after compensation doping, it is made by a p-type semiconductor of same amount of doping. Same amount of doping. Now, first I am writing. Okay, then what you want to calculate? What is the acceptor concentration that is needed for this? See, already we studied compensated doping. First, your material is n-type from this problem they given. So for this, it is electron concentration n into q into mu n. That is the value. After compensation doping, by adding Na to that, this A is converted into a n-type semiconductor to p-type semiconductor. That too, that Na should be greater than n. Now I am writing that is n plus Na. After adding some Na to that, it became p-type. Now it is p-type, and that too here Na is greater than n into q into mu p. Both are having same mobility, sorry, same conductivity they given. Now take Ni of silicon is 10 power 9 per centimeter cube, and mu electron and mobility of holes they given the values. Okay, now, and they given a mobility is not changing with respect to temperature. See, now equating these two. Now n into q into mu n, because both the conductivities are same. N into n plus Na into q into mu p. Now just get the q gets cancelled. Now n is equals to n into mu n. So mu n is 950 by mu p, taking this side it is 300, equals to n plus nd. Therefore n plus nd is, it is a 95 by 30, that is 3.16. It is a 3.16 n. Now nd is 3.16 n minus n, that is 2.16 n. Now the electron concentration in that one is, they given already amount of doping is, okay, they did not give any amount of doping. You need to calculate amount of doping from this side, from this data. See, sigma n is 1 milli 10 power minus 3 equals to n into q into mu n. So now n is 10 power minus 3 by q, 1.6 into 10 power minus 19 into mobility of electrons 950 they given. Just simplify this. So it is 10 power of 18, okay, sorry, it's 10 power 7 16, 10 power 16 plus this cancel, 10 power 15. So 10 power 15 by 1.6 into 95. That is 6.5 into 10 power minus 3. 6.5 into 10 power minus 3 into 10 power 15 per centimeter cube. So now it is 6.5 into 10 power 12 per centimeter cube. Just take that one, substitute here. So 6.5 into 10 power 12 per centimeter cube. So now it is 6.5 into 2.16. 2.16. Yeah, that is 14.06. 14.06 into 10 power 12 per centimeter cube. So they given, this is the option, 14.606 into 10 power 12. Okay, this is now we can write this one also, 1.4 into 10 power 13 per centimeter cube. This is the option they given. Okay, in terms of power 13 they given. So this is the one we get. So next problem. So you can expect this type of compensation doping. It is. A silicon sample is doped with 10 power 10 phosphorus atoms. Okay, 10 power 10 phosphorus atoms per centimeter cube. The meaning of that one is they given ND value 10 power 10 per centimeter cube. That is the ND they given. So at 300 Kelvin, calculate the electron and hole concentrations and position of Fermi level. So what is the electron concentration, hole concentration, and Fermi energy level you need to calculate. First point. Assume that the distribution of states in the conduction band is given by N of E into D of E. Here N of E into D of E it is. The meaning is N of E into D of E is 8 into 10 power 20 into square root of E dE. This is the distribution of states in conduction band. Okay, fine. Is expressed in electron volt. Calculate the number of electrons between the energy interval 1.9 kT and 2.1 kT above the band edge EC. Okay, first we complete this part, later we go to that. And okay, now see there is a point missing, that is a Ni value. So you can take Ni value for simplification. Let us I am taking Ni 1.5 into 10 power 10. Okay, 10 power 10 per centimeter cube I am going to be taking Ni value. Okay, or you can use exact value, no problem. So Ni of silicon we know that 1.5 into 10 power 10 per centimeter cube, because without Ni we can't calculate this one. Okay, so once you know Ni, now first point is ND is 10 power 10. So 10 power 10, ND is less than Ni value. Less than Ni value. Sorry sir, it is not 10 power 10. Do one thing, take it as 10 power 15. Take it as 10 power 15 because should be greater than Ni. 10 power 15. There is a value change. 10 power 15 sir. Now ND is 10 power 15. It is much greater than Ni. So immediately I can take electron concentration is approximately Ni. So ND, that is 10 power 15 per centimeter cube. Next I want to calculate hole concentration. So hole concentration is Ni square by ND. That is 1.5 into 10 power 10 into 1.5 into 10 power 10 by ND, 10 power 15. That is 2.25 into 10 power 5 per centimeter cube. Next they want to calculate Fermi energy level position. See, they given Ni value at the same time amount of doping. So from this no, and at the same time they added phosphorus. So this is N-type semiconductor. Now in a N-type semiconductor, the equation for Fermi energy level is EF minus EFI. That means EFN minus EFI is KT into ln of NT by Ni. This is the expression. KT, so you can take it 0.026 into ln of ND 10 power 15 by 1.5 into 10 power 10. So that is 0.026 into ln of A by B, ln of A minus ln of B. Okay, so that is this one cancelled in this by 10 power 5 times. So it is 5 into ln of 10 minus ln of 1.5. So 0.026 into 5 into ln of 10 is 2.3 approximately, minus ln of 1.5, 0.405, 0.4 approximately. Okay, 0.4 approximately. Now simplify this. 0.026 into 5 into 2.3 minus 0.4. It is 11.1 into 0.026. It is 0.288. 0.288 electron volts. That is the energy gap. So first part is completed, sir. First part, electron concentration we calculated, hole concentration we calculated, and Fermi energy level position we calculated. Okay, now I am going to completing the energy band diagram. Okay. So that energy band diagram I am going to complete. This is EC, EV, and intrinsic Fermi energy level is approximately midpoint of this, and Fermi energy level is somewhere here. Now this is EC, this is EFN, EFI, EV. So we know that this is 1.1 electron volt, and it is also 1.1 electron volt. This is 0.288 electron volts. Now that is a 1.1 my sorry. This whole thing is 1.1, sir. This is 0.55. It is also 0.55 electron volt. Now 0.55 minus 0.288, that is 0.262. This one, 0.262 electron volts. So this is the complete energy band diagram of a semiconductor what they given. Okay. Now I am going back to my problem. There. Next, what they want. See, he is giving here, they given distribution of states in conduction band. Distribution of states in conduction band is given by N of E into D of E. See, distribution of states they given N of E into D of E, N of E into D. Density of states N of E, D is the small distribution of small energy level. Fractional value of energy is given as 8 into 10 power 20, 8 into 10 power 20 into square root of E T. Yeah. So that is the given. Now what they want? Calculate the number of electrons between the energy intervals 1.9 kT and 2.1 kT. It means just take the energy band diagram. This is EC, EV. Calculate the number of electron volts, number of electrons number of electrons between the energy intervals 1.9 kT and 2.1 kT above the band edge EC. This is the band edge EC. Above this between 1.9 kT and 2.1 kT, total is 2 kT. In this 2 kT region, how many number of electrons are there? That is our problem. How many number of electrons are there? See, I know one thing. Total number of energy levels already they given. 2 kT they given. Okay. 2 kT already they given. Because 2.1 to 1.9 is 2. Okay. In that region, how many electrons are there? If 20, for example, in this 2 kT, let us I am assuming here I have 100 energy levels are defined. Now in this 100 defined energy level, how many electrons are there? If the probability of occupying the energy state or energy level in this 2 kT is, for example, 0.8 probability of occupancy, okay, then I can write 0.8 into 100, that is 80. 80 number of electrons are there. That means now I want what is the probability of occupancy in the region of energy level 2 kT. Okay, at energy level of 2 kT in this region, what is the probability of occupancy? For my easy understanding purpose, I am taking in this region, all these are in this region, throughout this region, probability of occupancy is same, all are similar type of junctions, regions. Okay, that means whatever the f of e probability function we have, this is constant in this region I am taking. So now you can take in this 2 kT region or above 2 kT, above EC you can take 2 kT, both are same. So 2 kT here means f of e is same in the sense the probability of finding the electron between 2.1 kT to 1.9 kT is nothing but a probability of finding the electron above EC 2 kT. Both are same because f of e is same, you are saying. Okay, that's why it is easy to me. Now I am taking that. So f of EC plus 2 kT is, or equation 1 by 1 plus e power e minus ef. So e value is EC plus 2 kT minus ef by kT. By kT. So first of all, you need to convert that energy in terms of kT. In terms of kT, you need to represent that energy. Here I am going to this. I want EC minus, there we will written EC minus, see this, EC minus EF. EC minus EF is 0.262 electron volts. Okay. Now 1 electron volt is equals to, or 1 kT is 0.026 electron volts. See, 1 kT is 0.026 electron volts, 1 kT value. Okay, so this is our EC minus EF value. So therefore EC minus EF is, how much you get? 0.262. So 0.262 by 0.262 by 0.026 kT. Now you get it. So that is 0.262 2 divided by 0.026. That is a 10.0, approximately 10 kt, that is approximately, that is 10 kt. Okay, that is a 10.076 I got. So 10 kt I am taking, EC minus EF. Okay, now I got the required value in terms of kt. Now substitute that one here. So now F of EC plus 2 kt is 1 by 1 plus e power EC minus EF. Just before we calculated 10 kt plus 2 kt by kt. 12 kt by kt, it is 12 e power 12. 1 by 1 plus e power 12. So e power 12. That is so compared to that one, e power 12 is the highest value. Okay, that is the e power 12 value. Okay, this is the value of f of EC plus 2 kt. By simplifying that, you get that value is approximately, it is 3.7 into 10 power minus 6. 10 power minus 6 into that is 10 power minus 6. That is the f of et. Now EC plus 2 kt. So far we calculated probability of occupancy only, we calculated. Now take this value, substitute in this. Now use this density of states here. Now therefore number of electrons, equals to electrons between 1.9 kt to 2.1 kt above EC is probability of occupancy in that region. F of E plus 2 kt, probability of occupancy into density of states. So that too only 1.9 kt to 1.9 kt to in between 2.1 kt. 1.9 kt to 2.1 kt into n of E into dE. That is the expression. Now just substitute the values here. So we got the value already. This is a 3.6 into around 10 power minus 6, you get 3.7, I think so. Yeah, 3.7. 3.7 into 10 power minus 6 to integral 1.9 kt to it is 2.1 kt into n of E value they given. So n of E value is 8 into 10 power 20 something they given. 8 into 10 power 20 into square root of E dE. 8 into 10 power 20 into square root of E dE. Just simplify this, not more than. So it is 3.7 into 10 power minus 6 into 8 into 10 power 20 square root of integral square root of e power 1 by 2, that is e power 1 by 2 plus 1 plus 1, it is 3 by 2. So it is 2 by 3 into e power 3 by 2 limits 1.9 kt and here it is 2.1 kt. Just take the values and simplify. That is 3.7 into 8, 3.7 into 8 into that 2 by 3 that is 2.98 into 10 power 15 by this into 2 by 3 into e power 3 by 2 by 1.9 kt. Okay, directly we can substitute this 2.1 kt. Okay, take this limit, substitute here. Now it is a 2.1 kt whole power 3 by 2 minus 1.9 kt whole power 3 by 2. That's it. Whole cube root for that. So just simplify. So you get approximate value. Okay, approximately by simplifying you get around 3.4 or 3.3 something into 10 power 12 per centimeter cube approximate. This is the electron concentration in that. Here you are going to using density of states above the conduction band and probability of electron occupancy in that energy levels. Okay, by calculating those two individually we multiplied. That's it. We done integration because particular energy in between particular energy levels they are asking 1.9 kt to 2.1 kt. That is the difference. Okay, now I'm moving to next one. Yeah. See this? An n-type semiconductor having uniform doping is biased as shown in figure. So this is n-type semiconductor. If external potential is applied, if EC is the lowest energy level in of conduction band and EV is the highest energy level of valency band, EF is the Fermi energy level, which one of the following represents the energy band diagram for n-type biased n-type semiconductor? See, sir, the meaning of this one is, let us take a semiconductor energy band diagram like this. This is n-type semiconductor. Now I am replacing the n-type semiconductor by its energy band diagram. It is EC. It is EF Fermi energy level. It is EV. Let us assume. Now this is subjected to external potential. Okay, that means this is connected to a external potential like this. An external potential like this. That too, it is negative, positive. It is negative, it is positive. Now, once the external potential is applied to this, the energy levels are going to be bending because number of electrons on this side is more compared to this side. Once electrons more at this side, average energy at this end is more. That's why here electron energy is increasing. So automatically EC also increasing. Automatically EV also increasing. This is the energy band diagram. That's it. EC, EF, EV over. So because simple thing, electric field is in this direction. This is the direction of electric field. Okay, now in the direction of electric field, they are going to be increasing their slope. So direction of electric field is this side. So in this direction, their slope is increasing. Okay, in this plot, this is the correct one. Okay. So for example, I am taking p-type semiconductor. Once I am taking p-type and I am connecting like this, it is positive, it is negative. So once it is positive, it is negative, electric field is directed in this side. Now energy level has to be bent this side. Now this is the energy band diagram after applying this polarity. EC, EF, EV. That's it. Because energy band electric field is in this direction, positive x direction. In that direction, the slope of that energy levels has to be increased. Simple one. Next problem. See. A p-type semiconductor sample with resistivity 40 ohm to centimeter at 300 Kelvin. See, it is a p-type and its resistivity they given. Okay. P-type semiconductor and its resistivity they given. So once it is a p-type semiconductor, sigma p, sorry, okay, equals to 1 by rho p. From this, resistivity is 1 by sigma p. So 1 by whole concentration into Q into mu p. They given it as 40 ohm to centimeter at 300 Kelvin. Is uniformly illuminated such with light that generates 10 power 3 electron hole pairs per centimeter cube per second. That is the generation rate is 10 power 13 electron hole pairs are generating per centimeter cube per second. For every second 10 power 13 new electrons are generating. That means electron hole pairs are generating. That much number of covalent bonds are breaking. That is the meaning of that. So, in steady state, calculate the change in resistivity of the sample caused by light. Only they want change in resistivity. See, simple. This is resistivity. Change in resistivity is delta rho. Delta rho. So, which is 1 by delta sigma. Which is 1 by change in hole concentration delta P into, that is a semiconductor. So in that electrons as well as holes we have. Okay, so I do one thing. I write first sigma. We go from first point. We know conductivity of a semiconductor is Q into N into mu N plus P into mu P. Okay, that is the equation for conductivity. Now, after applying generation, that means after applying illuminating your that material with light, this is the material we have. Now it is illuminated by a light. Generation rate is this much. So whatever the number of electrons increase, same number of holes are increasing. Delta N equals to delta P. So delta change in conductivity is Q into change in electron concentration, that is delta N into mu N plus delta P, change in hole concentration, into mu P. So but we know delta N equals to delta P. So now that is a Q into delta P into mu N plus mu P. That is the change in conductivity. Just take the values, substitute in that, then you get the conductivity. First you need delta P. To get the delta P, you have to take the extents of this series. From that, whatever the generation rate we have is delta, it is a p-type semiconductor. So delta N by tau N. For N-type, delta P by tau P you need to take, because minority carriers our intention. From this, delta N is G into tau N. G they given 10 power 13 into tau N. Lifetime of the electron lifetime are they given? Yeah, tau N they given 10 power minus 6 seconds. 10 power minus 6 seconds. 10 power minus 6. Now it is 10 power 7. Delta N is 10 power 7 per centimeter cube. Therefore, delta P we need, but delta P is nothing but a delta N, because Once one covalent bond is breaking, electron is coming out of that. So number of electrons is nothing but a number of holes generated. So it is 10 power 7. 10 power 7 per centimeter cube. Yeah. Now take that one, substitute here. Therefore delta sigma is Q 1.6 into 10 power minus 19 into delta P 10 power 7 into mu n plus mu P. They given mu n and mu P. It is 3900 1900. 3900 plus 1900. So it is 19. It is 789. So 10 power minus 10. 1.6 into 10 power minus 10 into, okay, 58. That is the change in conductivity. Now that is 1.6 into 58. That is 92.8. 92.8 into 10 power 10 ohm to centimeter inverse. That is the change in conductivity. Okay, but what they want in the problem, they want if light is switched off at t equal to 0, calculate the time period for excess conductivity to drop to 10% of its final value of t equal to 0. See, once light is switched off, already we completed generation and recombination of charge carriers. In that we got a standard plot. So this is the time. Initially, under steady state, minority carriers in a semiconductor is constant. Once your light is on, excess carriers are starts generating. Now charge carrier concentration is increasing, minority carrier concentration increasing. After some time it reaches the steady state. Now once you remove the light off here, so your light is off. Now it is going to be decreasing exponentially and finally it reach the steady state exponentially. Okay sir. Now if it is delta is p type, delta n, now the expression for this one is delta n into e power minus t by tau n. Okay, this is the point at where your light is switched off, but in this problem they given it as t equals to 0. Okay, now here delta n, okay, n is a function of time here. Okay, so delta n of t is representing it as, now I am representing this one, this part of the plot, it is delta n into e power minus t by tau p. Okay, now so what they want, at what time this is decreased to 10% of its maximum value. Okay, so that means this one by this one is 10%. So delta n of t by delta n is 10%. That means 10% means 1 by 0.0. Okay, 10%, 10 by 100, 0.1 equals to e power minus t by tau p. Okay, now e power t by tau p is 1 by 0.1, it is 10. Take natural log. Now t is equals to tau n, sir, it is t by tau n is ln of 10. ln of 10 is a 2.3. Therefore t is equals to tau n into 2.3. Tau n, they given it is 10 power minus 6 into 2.3. So it is 2.3 microseconds. At 2.3 microseconds, that conductivity is reduced by 10%. That is the problem what they given. Okay, and at the same time you need to get the, just a minute. So what they are asking, in steady state calculate the change in resistivity. Okay, change in resistivity we calculated. Once light is switched off at t equal to 0, calculate the time required for the excess conductivity to drop to 10% of its final value. We calculated. So both the values we calculated. Okay, so this is the problem. Okay, thank you. Thanks for spending your valuable time with me. So next session we go to the remaining part. Okay, so thanks for spending your valuable time. Don't forget to use my code VRAW10 during subscription and hit the bell symbol to subscribe and get the notifications. Please subscribe us and join our Telegram group to get the notifications about the upcoming videos. And please give your valuable comments on YouTube to strengthen ourselves and to provide a quality information to your upcoming friends. Okay, thank you very much. Thanks to one and all.